Hello, everybody. My name is Nate Fisher. I want to start by thanking the organizers, both of the conference and of this session, for doing what they did for organizing, and also for the opportunity to make these videos and share this work with you. And so today we're going to talk about stars at infinity in Teichmüller space. And in the first part of this talk, we're just going to focus on the first part of the title, the stars at infinity. We're going to think about metric geometry for a little bit. And then in the second part of the talk, we'll see how this relates to Teichmüller theory. Great. So the goals for this video is to first introduce some boundary theories for metric spaces. We'll define what a star is, what are the stars at infinity that Anders Carlson introduced in 2005. And then we'll look at a few examples of what stars at infinity are. Cool. And so first, let's think about boundaries. And why should we care about boundaries of metric spaces? Well, boundaries, like, in a lot of nice settings, give us a compactification of a metric space. And then when we're doing dynamics on compact spaces, we can get some nice results. And so some things that you can learn about a group or a space using boundary theory. You can learn about algebraic splittings of groups. You can classify isometries of metric spaces based on how those isometries act on the boundary. And there are plenty of results that work to understand the asymptotic behavior of random walks via this compactification and what happens in the boundary. And what are stars? What are stars in infinity? And so it's a very general construction. There's not much we need to assume about our space. All we'll ask is that we have a complete metric space and a Hausdorff fortification or compactification. And all the examples we'll look at will actually have a compactification of our metric space. And by fortification, we just want a space in which our metric space embeds as an open dense subset. And the idea behind the star structure is it gives us a measure of how well you can separate 2 points in the boundary by half spaces. And we'll talk more about the half spaces in a bit. And why should we care about this? And so the stars at infinity, this structure and the boundary kind of generalizes the Tietz structure that you get on the boundary of cat zero spaces. And in his original paper in 2005, Carlson was able to prove some cool things, some well-known results, but new proofs. For example, there's a star version of Hopf's theorem on ends, and also some ping pong lemmas for finding free subgroups in a group using stars. And so let's think about boundaries for a minute. And so one boundary theory that is commonly used in the world of geometric group theory is the visual boundary, or the Gromov boundary if you're in a Gromov hyperbolic group. And so basically what the visual boundary is, it's a way of parametrizing if you're sitting at a base point x naught, what directions can you look in? In which ways can you travel geodesically from your base point? And so the visual boundary we can think of as geodesic rays based at x naught, our base point, up to equivalence, where two geodesic rays are equivalent if they have bounded Hausdorff distance from one another, if they fellow travel forever. And so our first example of a visual boundary that we'll think of is the Euclidean plane. And so in the Euclidean plane, our geodesics are just straight lines. We'll fix our base point to be the origin. And so we have straight line geodesics. And if you choose two different directions, those straight lines will not have bounded Hausdorff distance. They will get arbitrarily far away from one another so they are not in the same equivalence class. And so each direction gives us a different point in the visual boundary, telling us that the visual boundary is a circle, a way of parametrizing all the different directions in which you can travel. Similarly, if we go to the hyperbolic plane, we have the visual boundary is a circle, and it's the circle that we draw when we draw the Poincare disk, for similar reasons as we just saw. And then a third example that we'll look at is the plane, but now with the soup metric, the L infinity metric. And soup metrics will come up in the second part of this talk, or second video. And so let's look at this example for a minute. And if we want to travel geodesically from the origin to P, one way to do that is via a straight line. Straight lines are geodesics in the soup metric as well. But this green line is also a geodesic. So is this, and so is this. And so there are infinitely many ways to travel geodesically from the origin to this point P. And when we look at the visual boundary of the soup metric, we still will get a circle. But because geodesics are not unique, when we try to put a topology on the boundary, things get kind of weird and we get a trivial topology. And for the sake of defining the star structure, stars at infinity, one of the very few things that we asked is for a Hausdorff compactification. And so if we have a trivial topology in the boundary, we aren't Hausdorff, and so that's not going to work out. So an alternative is to look at the Hora function boundary, and the Hora function boundary can be defined in a very general setting. You just need, you're not asking for much. We're looking at a metric space, and we won't define the boundary using geodesics, but rather just with the metric itself. And so we're going to embed our metric space into the space of continuous real valued functions on that space X. How will we do this? Well, we'll have an embedding iota that takes a point in our metric space and sends it to the function, which measures the distance between X and some input variable, and then subtracts away a constant where that constant, where we're fixing a base point, X naught. And so under very mild assumptions, this iota is an embedding, and then we take the closure in the space of continuous real valued functions under the compact open topology, and we call the Hora function boundary the set of points which are in the closure that we didn't already have, anything that's new. All right, and so now let's look again at the plane with this soup metric, and I'll just claim, and then we'll talk about why the Hora function boundary is also a circle, but we'll see that the topology isn't too bad. And so I claim that the Hora function boundary is a circle, and how do we get to the point north? We're just going to follow a geodesic straight up north, and one can show that you will converge to a function, and we'll call that function the northern Hora function. Similar for east, if we travel just east geodesically, we will get to a distinct function, a distinct point in the Hora function boundary. And the same thing for northeast. If we travel northeast, same thing works. And so we have these axial directions, and then the northeast, northwest, southeast, and southwest. How do we fill in the rest of the circle? And so there's a result of Carlson, Metz, and Noskov that says in this setting, any Hora function can be reached via a geodesic. And so we can ask what kind of geodesics fill in the rest of the circle. And so your initial guess might be, hey, let's try this straight line geodesic, just traveling not north, not northeast, but somewhere in between. Good guess. But if you go and do, like if you look at the embedding and look at the limit of the functions that you get via, like under this embedding, you'll find that this straight line geodesic will converge to the same Horo function as the straight north geodesic. And so this straight line geodesic will converge to north. So we're not getting a new Horo function on this circle. Instead, a way to fill in the circle is if we travel north for a little bit and then northeast, we will converge to a different function from north, a different function from northeast, and we converge under the compact open topology to a new function that lives in the Horo function boundary of this space. And you'll notice that these two geodesics stay bounded distance from one another. In the visual boundary, they would be identified. But here in the Horo function boundary, they lead to distinct points in our our boundary circle. And to fill in the rest of the circle, we'll do similar things. So if we travel east for a little bit and then northeast, we'll get some, we can like fill in the rest of this circle. And like the farther you go, the farther east you travel before going to the northeast. And we'll see that it will limit to just the eastern geodesic. Cool. So in order to define what a star is, we'll have to first define what a half space is. And so we'll start by fixing a base point in our space. And then for any subset V of our space, we'll define the half space, which is based at x naught, to be the set of all points which are closer to V than they are to the base point. For the general definition of star, we'll also need like a slightly different half space where we have this additive constant C, and it'll be the set of all points which are closer to the subset V than they are to the base point, up to some additive error. So let's look at an example. If we're in the Euclidean plane, we'll fix the origin as our base point. And if our set V is just another point, then we get this line of points which are equidistant from x naught and y. Anything to the right is closer to the set V. And so we actually get a true half space, like what we would think of as a half space intuitively in this case. Another example, still in the Euclidean space, but now with a different set V. We'll take V to be everything above, like anything where the y coordinate is greater than 2. Same base point at the origin. And then maybe like some flashbacks to high school geometry or algebra or functions. The set of points which are equidistant from a point in a straight line will carve out a parabola. And so we get this parabolic half space of points which are closer to our set V than they are to the point x naught. And so now that we have a grasp on these half spaces, we're ready to define a star, but first we'll define a base pointed star. And so we'll have a point in our boundary. We'll have a neighborhood basis of that boundary point. And so first, a star, which we'll denote as S, here it's base pointed. The star might depend on the base point, so we use this x naught to indicate that. Of our boundary point, we'll start off with a half space, the half space corresponding to the set V. We'll take its closure. We want stars to live in the boundary, so we take the closure to make sure that we're getting some points at infinity. And what we'll do is we'll take the intersection of all of these half spaces as we let V vary among all of the basis elements. So a priori, this definition could depend on the base point x naught, And so we will have a more general definition, but first, a quick example. And so in the Euclidean plane, with the visual boundary, we talked about how the north is like we could follow the straight north geodesic, and that gives us a point in the visual boundary. And to define a neighborhood basis, we could look at sets of this form, where we're taking like things above the absolute value function, but we're making the absolute value function steeper, and we're moving it up to infinity. So as a goes to positive infinity, we'll get these narrower and narrower wedges that are also moving up the y-axis to infinity. That'll give us a neighborhood basis. And like a nice little exercise is to see that the half spaces will have boundaries which are given by curves. But as a goes to infinity, those curves will get flatter and flatter and limit to just a straight line. So the half space will be everything with y-coordinate in it greater than some number. And so in this case, then we take the closure of those half spaces, look at all of the limiting directions in the visual boundary, and we'll see that the star of north in the visual boundary is just the closed hemisphere, the closed northern hemisphere, because our half spaces are going to have flatter and flatter like boundaries or limits. All right, and so again, that definition could a priori depend on the base point x naught. And so to get rid of that dependence, we're going to start off the same way. We have our boundary point, we have a neighborhood basis of that boundary point, and we're going to look at half spaces and their closures and intersect amongst all of the sets in that neighborhood basis. But now we're going to let that additive constant vary and go off to infinity, and then take the closure of that union of, uncountably many half spaces. And now our star is independent of base point. It's a lot to take in, but it is base point dependent. And we'll have nicer ways of computing stars than trying to understand what all of this means. So for example, as we just mentioned before, if we're looking at the visual boundary of the Euclidean plane, the star of any boundary point is just the closed hemisphere centered at that point. So the star of north is the closed hemisphere, the closed northern hemisphere. If we were at northwest, the closed hemisphere centered there would go from southwest to northeast. And so we can think of these closed hemispheres like we'll get like them rotating around the circle. For the visual boundary of the hyperbolic plane, one can show that the stars are singletons. And we'll call points which have singleton stars hyperbolic because they are kind of representing hyperbolic directions in your space. It's one way to think about it. And finally, if we look at the Hora function boundary now of the soup metric in the plane, it's a little bit different. And so in axial direction, so northeast, south, and west, the star is the closed hemisphere centered at that boundary point. So similar to what we saw in the Euclidean picture. But where things get different is in the non-axial directions. In non-axial directions, the star is the closed quadrant to which that point belongs. And so if we go look at the straight northeast geodesic that corresponds to this point here in the boundary, its star is the quadrant from north to east. But if we go north a little bit and then travel northeast, we get a point that's over here. and its star is still the same quadrant. This quadrant isn't moving or shifting. It's not going to be centered around this point. The same thing happens if we go slightly down, east and then northeast. Here, we're still getting a star that's the same quadrant. So yeah, any three of these points, any three of these Hora functions, points in the boundary will have this same star. And so what we're kind of seeing here, one way to interpret this is that the stars at infinity are putting a simplicial structure on the Hora function boundary of this suit metric. So our Hora function boundary is a circle, but let's think of it as a diamond. And then for this simplicial structure, Hora functions are like simplicial stars. So for north, the Hora function, or the star of north, will be the union of these two edges. Whereas for anything strictly between north and east, the star is just this one edge in the boundary. And this generalizes to higher dimensional suit metrics as well. We can view the star structure gives us a simplicial structure on the Hora function boundary for these suit metrics. Cool. A nice little fun fact. Stars have not been super widely explored. There's still a lot to understand about the star structure. But in like one of the questions is whether star membership is a symmetric property. It was an open question for a while, but Jones and Kelsey in a 2020 preprint found, they looked at the Hora function boundary of a d leader graph, and they found points alpha and beta in the boundary that showed that star membership is not symmetric. And so that's kind of cool, and maybe it's not too surprising. Metric spaces can be pretty crazy. And so since the star structure is defined just using the metric, maybe you would expect some weird things to happen in weird metric spaces. But this was the first example that was found that saw this asymmetry. All right, so that's the end of part one. That's our little foray into metric geometry and our introduction to stars at infinity.